give people an opportunity to ask questions about the lab, and if because I think most of you have started doing the lab, and I've had one or two questions, so I think there's a couple of things I'd just like to clarify before answer any specific questions. But as I'm doing that, perhaps you might have some questions. So what I'm going to do is go through some things that people have asked me about up to now this year, and then I'll and you can put in the chat some questions, or you can put your mic on and listen. So I'm just going to start. I'm actually going to put on the PowerPoint that I gave you a recording of, and just go through that a bit quickly. And I've done some extra diagrams to try and just help explain a couple of things that people have asked me about. Okay, let me just get my PowerPoint ready. Right. Okay. Yeah. Starting at the wrong place. Right. To just share the screen, of course. So I've just seen a question now as I'm doing my setting up here, which is more awkward than I wanted. Well, question: how can we get gradually varied flow in a 16-meter channel when we've been told it happens over 100 to 1,000 meters? So you can get gradually varied flow in any arrangement depending on the scale. So in a river, I probably should have qualified that. In a river, you're looking at distances of 100 to 1,000 meters, but it could. You can get gradually varied flow over a much shorter distance if you've got a much lower flow, which you've got in this particular channel. What I wanted to point out actually is in this channel, in short channels, you don't get uniform flow, which is confused a couple of people, and it's worthwhile just identifying that. So anyway, let me just get started on this backwater curve, backwater lab explanation. So yeah, I just need to move things so that I can actually see some chat questions if you've got any. So do type some in. Right. So backwater lab. I've got this general picture. What this is showing is that the got water that's coming in at this end, flowing down the channel, and flowing out the other end. There's that same channel. Water is going to be flowing. Actually, it's in this tank here and flows along the channel that way. And you've got a flow meter here that we can get some flow measurements off. So there's that same picture again. Flow's coming down here, and so I'm stood in the middle taking that picture, and now turn around, and I'm now looking down there. Obviously, it's not me taking a picture because I'm down there. I'll get onto that question, Natasha. Oh, oh. I'll get onto those questions later, Natasha and Charlotte. Let me just quickly go through this and just explain a couple of things towards the end. Right. So, what we've got upstream, we've got a sluice gate that is forcing the flow to be very low, about it was about 5 centimeters. This looks like about 2 centimeters. So it's forcing a depth, and it's forcing a depth that's less than normal depth. So it's less than normal depth, but it's less than the critical depth. So it's going to be critical flow here, given that flow rate that you've got in the lab sheet. At the downstream end, there's a weir which forces the depth to be higher than it would naturally be. So it forces it up here at about this level. You've got flow controls by a valve and a pump and a meter that tells you the actual flow rate. Remember, when you're doing the lab, and I pointed it out in the video, this is, and it's in the spreadsheet, this number is in meters cubed per hour, and you need it to be meters cubed per second. So it's an easy, you just divide it by 3,600, easy conversion. Some people asked about the vernier scales. So these are just pointers, so metal rods that are set at a horizontal, a zero value of horizontal water, and then we adjust this. We adjust this slider here so that we can take a reading of the water surface relative to a zero datum. And I'll just get onto that to explain it. So health and safety things, always wear your health and safety, your helmet, or think about health and safety whenever you're doing an experiment. You're doing this experiment, but always think about your health and safety. This is a picture of the hydraulic jump. It's a very weak hydraulic jump occurring in the channel. We can force it to, if we raise the end up higher, we'll get a steeper hydraulic jump. This is my picture of the sluice gate set at a few centimeters without any flow, and then I turn the flow on and it forces the water out to be coming out very fast under that sluice gate. So that's below critical depth. There's the same picture. There's a video that runs as a video. Right, I won't show it. Okay. And just behind that that sluice gate, there's a big tank of water that sometimes overflows into the lab, and you want to avoid that. At the downstream end, there is a weir that we can raise up slightly, and when water's flowing over it, it looks like this on the left and that on to the right. Okay, we're not interested in the water as it goes when it's outside the tank, but what we note is that you get if you did the analysis, you get critical depth going over that weir. However, we're not interested in doing the analysis of critical depth because all we're going to do is measure the height of the water. So, do you mention safety in the report? Well, if part of the report you're writing about how to undertake the lab, which would be very brief. You should also mention that health and safety should always be considered when you're doing a lab. And in this one, the two particular health and safety aspects, if you want to mention them, is wear a hat because it's easy to bang your head on the low beams, and be careful when walking on the raised um, raised walkway because it's easy to fall off. And any water on the floor you should clear up as soon as possible because it then becomes slippy. Just going to show, there's a picture here, a video here of the flow in the channel. So I've turned the water on, it's flowing down, supercritical where we can see it now. And over here at the far end, it's subcritical. It's deeper. It's actually deeper than what we could calculate as critical depth. If we went back a bit, just pause it there. We've got supercritical flow here and subcritical flow here and a hydraulic jump joining the two. What you've actually got at the moment, you've got steady flow coming in, set at a particular value, about 118 meters cubed per hour. But in the channel, you've got slightly unsteady flow because we've raised up the end and the hydraulic jump is moving upstream. So you've got unsteady flow for a short while, despite the flow rate going in is being steady. After a short period, when this hydraulic jump gets to about somewhere within this transparent walls, then the hydraulic jump stops because you're getting a balance of the energy losses, and it stops, and then you've got completely stationary. It's called stationary flow. Of course, the flow is moving, and the water surface moving. You've got steady flow. Okay, and it's that steady flow point that we're interested in when we're doing this, doing the lab. That's the hydraulic jump that we're measuring. We're trying to identify where it occurs and integrate the backwater shape of the hydraulic jump. What's important is that important to realize is the precision here. You're doing calculations in Excel to whatever, at least 3 decimal places, maybe many more. But you can see that this water surface is not very smooth. We can't measure to within a millimeter. We can't really measure to within a centimeter. However, we do try and make that measurement, and that's one of the things you can talk about in your discussions about accuracy. Here's a picture, not a very good video, of subcritical flow. The thing about subcritical flow is to get slight little waves going upstream, and the difference in supercritical flow, you get very little reflection, if none, and it's all going downstream. So this is the point I was making about the measurement of depth. I'm trying to measure the water surface here, and we see that it's jumping around a lot. In fact, on the next one, it's even worse when you get nearer the jump. We're trying to measure this to the millimeter, yet we see that point is getting submerged and then visible again. So think about those accuracy measurements. Right. There was a picture there that I'd sketched. I'll come back to this later. So let me just explain what the general arrangement was. And some of you might have worked it out from the video and and the Excel, but let me just say this again. This is the general arrangement. We've got a slope, we've got flow flowing down this way. We've got a sluice at one end forcing supercritical flow, and we've got a weir at the other end forcing subcritical flow. It's 16 meters long, 60 centimeters wide. We do need to work out what the slope of the channel is, and that's one of the exercises on the first tab of the spreadsheet. There's a tank just upstream which we pump water in, and that when we set the sluice to about 5 centimeters, we end up getting a water surface that looks a bit like this. So the aim of the exercise is to identify where this hydraulic jump occurs. I work out that distance or this distance. Okay, work it out theoretically and and then comment on why it's not, your answers are not perfect, and mainly down to data measuring ability. So trying to do that integration. If we had no weir, you would get supercritical flow coming down the channel. If you're to work out the normal depth and critical depth for this channel, for the flow rates that are actually in the experiment, you get you'll get a normal depth. Oops, it's not very good. It's meant to be a straight line. Normal depth about there, and you get critical depth above it. So for this particular channel, it's actually a steep channel. So you would get supercritical flow if it was long enough to have normal to achieve uniform flow, but actually it's not long enough for that. So we need to force supercritical and force subcritical flow. And in fact, on this particular channel, we're not, in this experiment, we're not at all interested in the normal depth value because we're not interested in uniform flow. And it's an important thing to remember. Uniform flow measurements are useful to know, but it's not always useful. What is useful is knowing what the critical depth line is, because we want to have subcritical and supercritical. We're designing it. Okay. So if we were then to increase the weir, so we increase the weir height, we get it interrupts that supercritical flow. It raises the water level. This goes above critical depth. So this is then subcritical. That jump moves upstream a little bit, more until it gets a balance in the middle, and that's the point where we're doing all our experiments. We need to then be able to measure the water surface. So first thing we need to do is, and this is explained in tab 1 of the Excel sheet, and this is what some people were a little bit confused about. What we do is we fill the tank, we raise the weir up as high as possible, fill the tank with water, and then turn off the flow. So there's no flow. That actually shouldn't be there at all. No flow in this. This is stationary. And we take a few measurements. I think I've got 16 measurements along there to work out that slope relative to the horizontal. So and I did that 3 times. Now they're not identical each time because it's actually a bit leaky, this weir. So the water dropped a little bit, and it's not totally stationary. It's not totally still water, because that would have taken ages to wait for. So things were moving around a bit. So there's 3 sets of readings for this for the channel slope, and you take the average of those. Then, once we've got the setup running, we've got a steady state. We'll use that relative height that we measured to measure the surface heights of along the channel. So that's all our experimental data collected, and that's what's on the spreadsheet. Okay, I'm just going to open the spreadsheet now. Where's the data? This is the exact same spreadsheet that you've got. Let me just have a look at these questions. So on the profile graph, so you're looking at this profile graph, Charlotte. Normal depth stays the same below the critical depth, even after the hydraulic jump. So, as I was trying to refer to, in fact, normal depth is irrelevant in this experiment. We're not interested in it. Because we never achieved normal depth. So what has anyone got a value for normal depth to give me? So if we were to put so 0.54 in there, that draws, oh, it's not right, is it? I know that. 0.54. So we've got normal depth in, and we've got a critical depth. Do you know what value of critical depth you got? I know it's I know it's higher than normal depth, so it's something like something there. I've just made that up. Okay, so I made it up quite well. 0.076. Okay. So all we're interested in when we calculate normal depth, or in this case, is to find out whether we've got a steep slope or a mild slope should uniform flow occur. But uniform flow doesn't occur. So normal depth is it's a distraction in this. What is of interest is critical depth, and to know whether we cross from below to above critical depth. That's the important thing. How come we had to work out 4 different types of normal depths if the Excel tab is not relevant? Because it's a useful exercise to calculate normal depths. And what it was showing you is that you have different ways of interpreting the SF term within the backwater calculation, because remember the SF term is dependent on the friction value, which is in the uniform flow equation. So while not the uniform flow equation is not actually used, normal depth is not actually used, the terms within it are used, and it's useful exercise. Okay. So this is the this is all the measured data effectively that we've got, and you need to do an integration from the bottom end, from a point at the downstream end, going to try and reproduce one of these three lines, or the average, or something similar, and do an integration from the upstream end going that way. Yeah, just looking at the chat. So I'm just going back to question of Natasha to check whether that was answered. In the Excel sheet provided, is the integration done direct step method or standard step method? Well, it won't be the standard step method because that's a bit fiddly, and I can't remember what it was. So okay, now I've said I think you should use the standard step method like we did in the direct step method like we did in the lecture the other day. This explanation here is more of a Euler method. You can work out which one you want to do. This, what I've got here, SF is that, FR is that, the DY. This is just a simple Euler method. If we're looking at that now, you might want to have a look at doing the direct step method. So in summary, we're not going to do this the standard step method. Okay. So I've got a question here from Aaron. How do we use the integration lines and the conjugate depth lines to locate the jump? Do we just draw a line between where they intersect? In fact, that is the case. I'm going to just going to try and write on that Excel form. I need to change my screen, so I'm going to just stop sharing a second and then share a screen again. So I've just got on my right on screen. Okay, so let's just think about the integration, and I'm going to do it on top of this this profile picture that we've got, because it's on top of this that you really want to get the picture. So and here you're going to start at this. Let's do the supercritical integration first. You're going to start at this point. Now you'll find in the integration what is crucial to get that height pretty accurate, because it will change the position you're interested in getting a conjugate depth line. So you then do some integrations, and your integration will go along here, and you'll get a nice smooth line. And you'll find that it's quite similar to this supercritical line, because it's very this is very flat. So we get a line here, and you can do your integration. Right, you can go a bit further than where it's going, because you don't know where it's going to, and you can do an integration starting at the downstream end, going backwards this way, and they won't be exactly on the same points, but it'll go something like this. So you've integrated a line like that, and then you need to work out your conjugate depth line to each of these. So the conjugate depth line is using the well, y1 over y2 equals half square root 1 plus 8 f r 1 squared minus 1. Is that right? Okay. So if this is your y1, what? Hmm, this is y1. Oh, it's not letting me draw on the graph now. Okay. We want to get a y2 line. That's y1. You need a y2 line which goes like that. And using the other conjugate depth equation, you can get an equivalent y1 line. So if this is your y2, this is your y1. You get a y1 line which goes like that. And when where this point crosses here, or that point crosses there, they should be in the same place. So your jump is there. And it will be a vertical line, not a sloping one, because we haven't looked at working out the length of a jump. That is possible, but we're not going to do that. So what I've sketched on here is really what it is what you have to do with your integrations. And you should get very slightly different answers between your Mannings and your Chesney. And depending on what depth you use to convert Mannings to Chesney, you'll each get slightly different answers as well. Is that okay? Anyone else got any questions? So, should we have lists of figures and tables? No, don't bother with that. It's a short report. Doesn't need a long list. Doesn't need a table of contents or a list of figures and tables. Do reference things. Some people ask me if they're going to include a snapshot from the video or something from the lab, and just do put a reference in, just to say from supporting material for the lab with my name, just so that you get used to referencing things that are not obviously formally referenced. As to Alexander, for the analysis, do we have to explain why we choose the initial values for determining the normal depth? Just say what you did. What would be more interesting is to say how sensitive the results are to the choice. And when I say sensitive, I mean, in the end, how far does the changing your initial values, how much does it affect this range of where the hydraulic jump may occur? Well, then your 10-page limit, you can put things in the appendix and you won't get marked down for it. I don't want a 20-page report now. I'll read the 10 pages and maybe look at something if it's referred to in the appendix. One of the key things about writing a report is to be concise, but it as and short and precise as possible, so that the whole message is told within that within as few words as possible. But the whole message should have just enough and no more. Okay. So for the theory section, not sure what you should write about. Well, what have we done here? We've integrated a backwater curve. So you could just mention what the backwater curve is, and you could mention what the backwater curves come from an energy consideration, and it shows how depth is changing as it goes down the slope. You could say that you can have two different depths for specific energy, and those correspond to sub and supercritical flow, and that hydraulic jump equation that I've got on the screen there is can be derived from that for a rectangular channel. And that the objective of the exercise says in the lab is to locate to verify this gradually varied flow equation, and to identify and use it to identify where the hydraulic jump occurs. And in identifying that, will help you we're assuming it verifies the equation. Don't worry about going into too much detail. In fact, don't go into too much detail. Let's say don't want a derivation from scratch of the gradually varied flow equations. You've got 10 pages. It's the analysis and how you use the analysis. It's just much more important. The theory just copied from the notes, so it's not showing me what you understand. Anyone else got a question? I answered everyone. Have I missed anyone? Just going back now to the list. No, I can't see any other questions I've missed. Right, I'll finish there now. If you do have any questions, then send me an email. I'll try and respond quickly. Got a class tomorrow at 10. I'll see you all there. Remember, you've got to submit this in a week today. That's the 22nd of a week tomorrow. In fact, 22nd of November. Okay, thanks.